All right, in this module, we're going to talk about some of the different configuration that our molecule or macromolecule polymers can have. And so we're talking about the arrangement of the end groups. And the first thing that we're going to talk about is tacticity. And this is known as stereoregularity or the spatial arrangement of the R group. So again, if we talk about a vinyl polymer and we have polyethylene, but one of those is an R group, so it's something else. And we want to look at where those R groups are. So in this case, the R groups are all on one side, right? So all R groups are on the one side. This is called isotactic. So basically, spatially, they're all on one side. They're the same side. And so, again, this isn't an accurate representation of what it would look like. So if you kind of show the zigzag and the bonds here, you'd see that R's are all on one side. Another type of tacticity that we can have is known as syndiotactic. And this is where we alternate the R groups. So this first repeat unit, R is here. The second one, it's on the opposite side and vice versa. So it keeps alternating. And so syndiotactic is when we alternate. And so you can see the alternating on this side. And we can also have a tacticity where they're randomly positioned. So you see a couple here and then it flips and it's just randomly as you go throughout the chain. And this is known as atactic. So kind of not arranged spatially in a repeating manner. So those are kind of the three tacticities that we can have. All on one side, alternating, or randomly positioned. Also, in terms of configuration, we can also look at cis and trans isomerisms. And so this is where we're looking at specific groups and what side of the chain they're on. And so if we want to, a good example of this is natural rubber, which is isoprene or cis isoprene. And so in this case, we have a carbon double bond. We have a CH3 group and a hydrogen group, and they're both on the same side. So it's cis. So same side, cis. And the same material, but instead of those groups being on the same side, they're on alternating groups. This would be trans isoprene, and it's a whole different material. So it can greatly affect the properties. So the hydrogen atom and the CH3 group are on opposite sides of the chain. All right, so let's go through a quick example, or let's go through a quick quiz question about this. And what I want you to think about is, what do you think the effect of tacticity is going to be on the polymer's properties? So you see, maybe think about a specific property and think about how it relates to that, a relationship with that property. So see what you think of. This is kind of a brainstorming opportunity. So think about how that tacticity, so isomerism or the syndio or isotactic, and see how you think that would affect a property. And then do that on the quiz and come back and we will discuss. All right, so let's see what we have. And so what I can kind of give you there is just in general, the least regular and the least predictable tacticities tend to give poorer packing of the polymer. So that leads to lower density. It also leads to low strength and stiffness, and also poor resistance to heat and chemical attack. So basically, it comes back to kind of regularity of the polymer. So if we go back to let's go back to the tacticities here. So this, where all the R's are on the same side, is very regular. Where they're alternating is very regular. It's easy to predict where the R's are going to be. However, atactic is very random, and you don't know where a given R is going to be. And so that's saying that atactic would be the least regular, least predictable, and give you poor packing, low density, low stiffness, low strength and stiffness, and then poor resistance to heat and attack. That's kind of the general properties. We're going to talk more about various functional groups and ways that a molecule is arranged and how that affects its various properties in the sections to come.